Right, this is the second part to video to do with momentum and explosions. Apologies, some reason the sound went a bit weird in the previous video. No idea why, but I'm 16 minutes in, so I'm not going to record that one. Anyway, this one here, the correct answers. Total velocity of the spacecraft and rocket gases are always zero. Well, that is going to be wrong. And the reason why it's wrong is, aren't those gases going to escape at a very, very, very high velocity? Oh dear, put that in different color pens so you can see it. They're going to go at a very, very high velocity. And this one is going to have a lower velocity. And it's all to do with mass, because the mass of this is going to be large and the mass of the gases coming out is going to be small. Momentum before must equal to momentum afterwards. The weight of the spacecraft is less than the downward force of the accelerating, force of the accelerating the rocket gases. Well, these gases are going down, okay, and this is all to the fact that the weight of the rocket going down here is going to be W. Well, this is the force of the gases coming out, which creates an equal opposite force of the upthrust making the rocket go up. Well, that upthrust must be greater than the weight, otherwise this rocket's not going up, is it? Therefore, that is true. The kinetic energy of the rocket gases provides the upwards force on the spacecraft. Well, there's nothing to do with kinetic energy whatsoever. Kinetic energy is not a force. Therefore, energy is a different concept going through here. No, it doesn't. The rocket gases must hit the moon for there to be an upwards force in the rocket. No. You can have no moon here whatsoever, and it will still move away. If you've got, example, going to the moon, you've got the rocket middle of nowhere between the moon and the Earth. If you blast out the gases in one direction, won't the rocket start to move? So that's wrong. And then finally, the total momentum of the spacecraft and the rocket gases remain constant as the gases are ejected. Well, that is true. Momentum before must be equal to momentum afterwards. Conservation of momentum. So the true answers are that one and that one. I hope you got them correct. Okay, so to finish this all off is we were here. This will come in. And there is an exam question in the chapter about this, or about momentum, but this is mainly going to come in into when you get in year 13, we look at nuclear decay. Now, you know about these already, and this is alpha decay. Now, in the case of alpha decay, you know it's going to be, what's the black pen? Let's first rub this out, get rid of that. Back to my black pen, hopefully. Got black pen? No. Still in red pen. There we go. Is, you know, your alpha particle is going to be a 4-2 helium nucleus, which there's a 4-2 here. Now, this is all alpha decay. Now, I'll give you an example of alpha. You can have 229 and 90 is going to be thorium. Now, when it decays, you get an alpha particle, and also then you're going to get your 225 radium. And that's going to be 88, because 225 plus 4 makes 229, and then your 88 plus 2 equals your 90. Remember the conservation here of looking at the number of nucleons, i.e. number of protons and neutrons. Now, in the case of here, it's like a mini little explosion, because your alpha particle goes this way, and your nucleus goes in the opposite direction. We call this a nucleus recoil. And it recoils way up to here, because here I'm going to have my radium. It's going to go in the opposite direction to the helium, or alpha particle. Now I'm going to go into my red pen. Well, first of all, I'm going to rub all these out. Getting back into my red pen, yeah, it's working. Is this one must have a large mass, and the helium nucleus must have a small mass. Therefore, you've got conservation of momentum happening again, like an explosion. Therefore, when they move away, won't this have a velocity that must be large, and that velocity must be small? Because now you must have the momentum going this direction must be equal to momentum going that direction. So hence, if I did the mass of the radium and call it MRA, and then I had my mass of my helium, this one would have a velocity, and the velocity of this one must be small. This one must have a velocity and must be large, because they must balance out. And again, it will do it in the ratio of the masses. and you're going to see exam question on that. Now, here's going to be an exam question, and I'm going to probably make a separate video of this because these are going to be on your end of chapter questions. Now, we're going to put in a post in Edmodo. Here's going to be all the exam questions. Now, it comes up in the textbook, in the old textbook. It's in chapter 1. And what we're going to ask you to do is go through all these questions, and you'll find, I think this one is question 6, which is down, there you go, it's here. Now, those we want you to go through, and you'll find it in the video. I'll give you a worked answer as well. Also, you'll find these at the end of chapter, and you'll find these are in your textbook, the old textbook. You'll find these on, I think they're on, trying to find the page number myself now. They're on page 17. What it is on the new textbook, I've no idea, but we'll put a PDF copy on Edmodo for you as well. And we'd like to answer these, and we'll also put worked answers for you onto Edmodo. So to recap, what you should be able to do now is you should be able to apply the conservation of momentum to explosions and also calculate the unknown velocity of an object after explosion. Enjoy the video.